Hello there. In this video, we are moving on from defining different properties of services, and now we're getting into routing. And routing in the CubePython package is basically after a customer or unit of flow has finished its service, it's going to go somewhere. It could leave the network entirely, or it could go to another node. How does that decision get made? And even if it goes to some other node, when there's multiple candidate nodes it could go to, where does it go? So routing is all about defining that pattern of where customers go after their service is complete. So we're going to try just going through the documentation this time. Um, it just seems like a thing worth trying. So let's talk about how to define routing with a transition matrix. So transition matrices, just before we even get into reading, are a lot like stochastic matrices, but in Q, they do not have to have rows that add up to 1. Instead, just the amount of probability among the other nodes has to be specified, and the complement of that is assumed to be the probability of leaving the network entirely. Okay, so let's jump into this. There are a number of methods of defining how customers are routed from one node to another after service. This is done with the routing keyword when creating a network. So one common method is by defining a transition matrix, common when defining Jackson networks. A transition matrix is an n by n matrix where n is the number of nodes in the network such that the ith jth element corresponds to the probability of transitioning from node j after service at node I. So for example, in a 3-node network, a transition matrix might look like this. We've got the first row, which is for the first node, defining the probabilities of where else it goes. And here, this 0 probability means that after completing service at node 1, there's a 0% probability of going right back into node 1. Instead, there's a 30% chance of going to node 2 and a 70% chance of going to node 3. And if a customer is finishing its service at node 2, then there's a 0 chance that it returns to it. There's also a 0% probability of going back to node 1. There's a 100% chance of going to node 3. And then in that last row, we've got that if a customer has finished service at node 3, there's a 0% probability of going back to node 1, a 0% probability of going back to node 2, but a 20% chance of going back to the same node, node 3. This is where you can see the complement in action, that there's an 80% chance of leaving the network entirely. So let's go through what their description of this is. This represents that customers finishing service at node 1 enter node 2 with a probability of 0.3 and the node 3 with a probability of 0.7. I think there's a little typo there. Customers finishing service at node 2 are certain to enter node 3, that's that probability of 1, and customers finishing service at node 3 re-enter node 3 with probability of 0.2 and with probability of 0.8 leave the system entirely. So in Q, there are two ways to define this, with a list of lists or a routing object. And there's actually some different kinds of routing objects that we'll get into as we go through the documentation. But in this video, we're sticking to the transition matrices, which there's basically just the two ways. So the first way is to have a list of lists. To define this list of lists, we can use this example. So a lot of this should be familiar if you've watched the other videos of going, you have to, for this particular network where there are 3 nodes, you have to define arrival distributions for each of them and service time distributions for each of them and the number of servers at each of them. And then this routing matrix that says these probabilities as were specified in the example above. There's our 0.3, 0.7, our oh, this must be a typo. No, it's not a typo. It's just a different example probably. Or it's a typo. Let me see, because it's supposed to be 1.0. Nothing says it actually is the same example, but I would have thought this would be 1.0 to follow with the example above. But anyway, this is actually also a valid network. So there's if you finish your service at node 2, there is a 90% probability of leaving the network entirely and a 10% probability of going to node 3 for this particular example. Great, so then we've got this routing object option. To define with a routing object, we can make use of the built-in transition matrix routing object and give it a list of lists as above. Immediately, I'm not sure what the benefit of this is. This is a API change that happened earlier this year or last year, I can't remember. And I'm not sure what it's for, to be honest, but you could, I guess, look more into the attributes and methods. I'm not sure what this adds that the original matrix passed as a list of lists doesn't have, but that's okay. So routing objects can be more flexible than this, allowing logic-based routing in addition to probabilistic-based routing. For more information, we'll get to the other stuff that happens later for defining custom routing objects and stuff like this. But suffice to say, this gets us started with saying that there's some constant or stationary, if you will, probabilities of transitioning from one node to another, or correspondingly leaving the network entirely. So thanks for watching. Hopefully that's clarifying for you on what these transition matrices are about in discrete event simulations of queuing systems, and I will catch you in the next video. Take care.